Hi there, Dr. P here, and in this lecture video, excuse me, I'm going to talk about carbon-13 NMR spectroscopy. Now, the NMR spectroscopy that we've talked about so far has been proton NMR. And NMR signals for protons tend to be pretty strong because, well, protons are by far the most abundant isotope of hydrogen. It turns out other nuclei can be NMR active as well. One of those is carbon-13. Now, carbon-13 only accounts for about 1% of carbon atoms in nature, so it's not particularly sensitive. In fact, for the Nanalysis 60 megahertz machine that we have, if we had gotten one that could do carbon-13 NMR, it would take probably around 20 minutes to take a natural abundance carbon-13 spectrum. So instead of taking a minute and a half, it would take 20 minutes. So the sensitivity is a big difference between proton and carbon-13 NMR. We also have some of the features of the spectrum. When we analyze the spectrum, those will be different as well. For example, in proton NMR, we of course have the chemical shift, splitting, and integration. And those of course give us the peak identity, or rather the chemical environment for the shift, how many nearby protons there are for the splitting, and the relative numbers of protons for the integrals. But in carbon-13 NMR, we're only going to look at the number of signals and the chemical shift. Now, why is that? Well, if we had a spectrum, carbon-13 spectrum, and we didn't do anything else to it, we would get proton-carbon splitting. There would be splitting from protons attached to carbons. So let's say you had a carbon, it could be something like this. So let's say we had a carbon with a hydrogen, and then maybe attached to another carbon with that hydrogen. I don't know, that's attached to other stuff. So this carbon here will be split by these two hydrogens that it's attached to. And it'll be split by the hydrogens on the next carbon over, and potentially the next carbon over here. So it can give very complex splitting. And, in this case, the spectrum may be considered unreadable. So what we do instead is we run what's called a decoupled spectrum. And we can irradiate at the frequency for the protons and basically remove them from the spectrum, just kind of erase them, if you will. And that removes all the splitting that we would get from the protons. So that's a nice thing we can do. We can decouple. Now, another interesting thing is that for the vast majority of C13 spectra, all of the signals are singlets. Let's think about that for a minute. Why would that be? Well, we've decoupled things, so we don't have any hydrogen-carbon coupling. So the protons won't make the carbons split into multiple signals. Also, we have very few carbon-13 atoms. Remember, carbon-13 is only about 1% of carbon atoms. So with fewer carbon atoms, it's less likely that there will be two carbon-13 atoms next to each other, and we won't get splitting. So a typical carbon-13 atom will most likely have carbon-12 atoms next to it, and carbon-12 doesn't cause any splitting. Now there's some other differences. We have a different frequency of energy required. So for example, our 60 megahertz proton NMR in the lab would be I believe a 15 megahertz carbon-13 NMR. So it's just a little different there. Also, and we'll use the same reference, TMS, but the signals appear over a much larger chemical shift range, 0 to 220 ppm. And just as we had with protons, each signal in the spectrum represents, in this case, a carbon with a unique chemical or electronic environment. And like with protons, if we have any kind of symmetry, that can cause carbon signals to overlap if they're symmetric carbons. So we can see that in the following diagram. So let's say we have orthoxylene. This is orthoxylene. The two methyl groups are ortho to each other. We have a plane of symmetry down the middle. So we have 1, 2, 3, 4 types of carbon. This guy's the same as that one. That one is the same as that one. That one's the same as that. And that last guy is the same as that. So we have that plane of symmetry. So 1, 2, 3, 4 types. We should get 4 signals. For metaxylene, we have a plane of symmetry down the middle, and we should have 1, 2, 3, 4, 5 types. These two along the axis are their own, each of those is its own type. This one here is the same as that guy. That one is the same as that. And the methyl groups are the same. So we should get 5 signals. For paraxylene, we would only see 3 signals because we have 2 planes of symmetry. We have one here and one here. So our methyl groups are the same. The carbon that the methyl group is attached to is the same. And then this carbon here is the same as that one, and that one, because we have the 2 planes of symmetry. So we should only see 3 signals. So just as an example, let's take a look at the following molecule here. Now, how many chemical shift signals, how many C13 signals should we observe? Well, let's see. We've got planes of symmetry. We have one down the middle of the CO double bonds, and then we have one here as well. So we should see, maybe I'll circle them in green, or no, maybe I'll do a little highlighter here. Yeah, we'll highlight here. We should get one there, but that's the same as that guy, which is the same as that guy and that guy. So that's one type. And then the carbonyl is the same as that carbonyl. So we should get 2 types. So 2 types carbon equals 2 peaks in C13 spectrum. Oops, I seem to have run out of space there. I'll abbreviate. There we go. All right, so let's go ahead then and take a look at where these peaks may show up. Remember, in proton NMR, if we're close to an electron withdrawing group, or if we're close to, say, a double bond or an aromatic ring, we're going to be further downfield. Protons attached to aromatic rings are around 7 ppm. Aldehyde protons, because they're right next to the CO double bond, are way down between 9 and 10 ppm. Carboxylic acids are 10 to 12 ppm, etc. So we have similar general trends, only over a much larger range. So for example, we'll have carbonyl carbons will be somewhere in the 180 to 220 region. Double bonded carbons, sp2 carbons, whether they are aromatic or alkenes, will be in the 100 to 150 region. Triple bonded carbons, and then carbons bonded to something electronegative, such as nitrogen, oxygen, or a halogen, will be in the 50 to 100 region. And then aliphatic carbons, that is, carbons bonded only to other carbons or hydrogens, will be between 0 and 50. And typically methyl groups, just like they were in proton NMR, will be the most upfield. So, maybe around 10 ppm, 15, 20 ppm. All right. So again, we can take a look at, say, this example here and try to predict the number of signals and chemical shifts in the following NMR spectrum, or the NMR spectrum for the following molecule. Now, there's no symmetry here, okay? There's no planes of symmetry, however we cut this. I mean, there is a plane of symmetry because the top and bottom, or the front and back, look the same, but that's the plane of the screen. So let's see. I would expect, so around 200 ppm for those guys. And then that's probably around, I don't know, around 120 maybe? Around 120. I'm just choosing numbers in the middle of the region. That guy there is probably around, because it's kind of close to the double bond there, so maybe we'll say 25 or 30. So I'm going to say 25. That guy's probably a little more downfield because it's kind of closer to the carbonyls and stuff. So maybe we'll say, I don't know, 40. And that guy might be around 40. And I think that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are our 9 carbons. These are just estimates. So we're going to use carbon 13 NMR as another tool, another piece of the puzzle to help figure out structures of molecules, such as your unknowns. Okay, now we actually can get more information than just the number of signals and their chemical shift. We can do some experiments where we introduce a little bit of carbon-carbon coupling, or rather carbon-hydrogen coupling, back into the system. And that's what's called depth spectroscopy. DEPT stands for distortionless enhancement by polarization transfer. NMR spectroscopists like to come up with all kinds of acronyms for their spectra. Of course, we've got DEPT, we have APT, we have INEPT. Let's see, we have COSY, we have NOSY, we have ROSY. Let's see, we have TOXY. When you get to multidimensional protein NMR, you've got names like HO-HA-HA and stuff like that. So anyway, just a few little side story there. Yes, I did a lot of NMR spectroscopy as a postdoc. All right. So in the DEPT experiment, we'll run several spectra. The first one is fully decoupled, which shows all the carbon peaks. The next one is what's called depth 90, and the 90 refers to the duration of one of the pulses for acquiring the spectrum. So the spectrometer is going to do some stuff to make only certain things appear. So in this case, with depth 90, we only get CH signals. And then with depth 135, CH3 and CH will give us positive, but CH2 will give us negative signals. So what does that look like? Well, this is the general trend here. In a decoupled, fully decoupled spectrum, regardless of whether we have primary, secondary, tertiary, or quaternary carbons, so a carbon with only one other carbon attached and 3 hydrogens, that's primary. 2 carbons attached and 2 hydrogens is secondary, etc. All of these guys will be positive in our regular decoupled spectrum. That's kind of our default spectrum. In the depth 90, only the CH, the tertiary carbons, appear, and they're positive. And in the depth 135, we don't see any quaternary carbons. The CH carbons, the tertiary carbons, are positive, and so are the primary carbons, the CH3s. But CH2 show up as upside down negative peaks. Now, I know I went over all of that, and we'll look at this example here. I will say that the spectra that I provide you for the unknowns lab are just the broadband decoupled. So you don't really need to worry about the depth 90 and depth 135, except for maybe practice problems. Anyway, we could go ahead now and take a look here and say that, we could distinguish between these two isomers here. These are constitutional isomers. And here we'd have, let's see, well, maybe I'll highlight them in different colors here. So let's go with yellow. So I'll highlight my primary carbons in yellow, my CH3s. I don't have any, so I won't highlight them in yellow. I'll highlight my CH2s in yellow. Here's one, and there's one, there's one, there's one, there's one. Here I also have, there we go. And then I've got my CHs here and here. So now looking at this, we can say, oh, I've got 1, 2, 3, 4, 5 CH2s, and I have 5 CH2s here. But one of the keys is that their chemical shifts will be different. This carbon will have a chemical shift around 60 or 70 ppm because it's attached to the oxygen. So in our depth experiment, we'd expect our CH2 to show up as negative in the depth 135. So we would see a negative peak. And let me write that down here. Negative peak in depth 135 around 60 to 70 ppm. Here we have a CH. Well, CH gives us a positive peak in depth 135. So we'd have a positive peak in depth 90 and depth 135 around 60 to 70 ppm. Oops, sorry about that, ppm. There we go. So based on what the downfield peak, so where the carbon that's attached to the oxygen, where that shows up or how it shows up in the depth 90 and depth 135 spectra, we could differentiate between these two. So it can be useful. Mostly we're going to be focusing just on the regular decoupled carbon-13 NMR spectra. I wanted to close this with talking about MRI, magnetic resonance imaging, because it's really a cool technique and it makes use of the nuclear magnetic resonance phenomenon. It's called, there are two reasons why it's called, or two stories as to why it's called magnetic resonance imaging and not nuclear magnetic resonance imaging. And one is that people are afraid of the word nuclear. I mean, you drive around Berkeley, the city of Berkeley, and there's a sign saying nuclear-free zone. It's like, well, okay, all atoms have nuclei, so really Berkeley is not free of nuclei. Anyway, so yes, people are afraid of the word nuclear or atomic. The other one was that actually radiologists wanted to have MRI as a technique that they used, along with x-rays and CT scans and stuff like that, and they didn't want nuclear medicine specialists to claim it as their own. Nuclear medicine specialists is kind of a less common specialty. They're the people who administer radioisotopes for treatment of cancer and stuff like that, which we can talk about more another time. Anyway, MRI makes use of the magnetic resonance phenomenon because we have a lot of water in our bodies. And so the body is actually analyzed in a big, not a tube, you don't get put in an MR tube, but you do get slid into a cylindrical coil. And different tissues will show up differently depending on like how much water versus fat they may have. and you can produce a 3D image using a magnetic field gradient. So the field is not homogeneous, it's not even all the way across the body. And that allows you to spatially address where signals are coming from. So you can tell, oh, this is from, the right hip, and this is from the left hip. And so you can orient things. And then, and there are different types of MRI scans that are done. And will, you can generate an image from those, and they all kind of look a little bit different. I've had an MRI done of my shoulder. My wife's had several done of her back. And the different scans sort of have different things that they resolve better than others. And one last thing here, this slide asks, are there any known side effects from exposure to either radio waves or a magnetic field? Basically, no, unless you have a pacemaker or some, an aneurysm clip or something, large and ferromagnetic in your body. You'll be just fine. All right. Well, on that note, I'm going to sign off. Feel free, of course, to print out your C13 NMR spectra, or just download them and bring them to lab or office hours, and I can help you analyze what's going on. All right, well, until next time, stay safe out there.